We're going to start now a sequence of videos that are going to go over linear functions and linear modeling. So we're going to start out with just a brief introduction to linear functions and their graphical representations. So a linear function written in what we call slope-intercept form is a function that has the form f of x equals mx plus b. So f of x equals mx plus b. And m and b are just real numbers. The m is called the slope of the linear function, and the b is the value of the y-intercept. And these are both ideas that we are going to talk about more in depth as we get into the sequence of videos covering this topic. So we're not going to say too much about the slope and the y-intercept at this time. As long as the slope isn't 0, the domain and range of a linear function will always be negative infinity to infinity, and the graphical representation of a linear function is always going to be a straight line in the xy plane for the purposes of this class. This is a GeoGebra image, so we know that we need to assume that this line goes forever in both directions. This linear function has some key features to look at and think about. So one, we want to notice as we move from left to right along the input or x-axis, the graph in this case goes downhill. And what we're going to discover as we go along is that when we have a graph that has this downhill motion to it or goes downhill from left to right, that the slope is always going to be negative. That's going to be a key feature of these graphs. These graphs have intercepts. In this case, I have an intercept, or a place where I intersect the y or f of x axis, and I also have a place where I intercept or intersect the x or input axis. So this point right here is called the x-intercept because it intercepts or intersects the x-axis. And we want to notice that the ordered pair here is input 4, output 0, and the hallmark of the x-intercepts is that they will always have a y-coordinate or f of x coordinate of 0. So we want to remember our ordered pairs are going to be x, y, or input, output ordered pairs, or in this case x and f of x, because we want to remember from our previous discussion about functions that as long as we're working with a function, y and f of x are synonyms. They're used synonymously. This point right here where we cross the y or f of x axis is the f of x intercept or the y-intercept of our function, intercept. And it has the ordered pair input 0, the output is 3, and a hallmark of a y-intercept or f of x-intercept is that the x-coordinate will always be 0 as you cross the vertical or output axis. Something else to notice here is that the 3, we have this function here, it's in the form, this is in slope-intercept form is m x plus b, so in this particular case b is negative 3/4, m is negative 3/4, and the b is 3, and this 3 right here is corresponding to the value at which we cross the vertical or input axis, and that's always going to be the case. This value for b is going to give us the value at which we are crossing the vertical or input axis. When we look at the arrows on the end of the graph, we see that the x-coordinates are running infinitely far to the left, and from this arrow down here, they're moving infinitely far to the right. So we see that for this linear function, the domain is x is an element of the open interval from negative infinity to infinity. And that's what the first slide was indicating. As long as that slope isn't 0, it's always, both the domain and range should always be negative infinity to infinity. We just want to drive that home. This arrow here on the linear function has both a horizontal and vertical component. The vertical component is going towards positive infinity, and over here the vertical component of the linear function is going towards negative infinity. So we see that the range of our linear function is going to be the outputs, or the f of x values, are also going to run from negative infinity to infinity. The graph of a linear function can also move uphill as we move from left to right along the input or x-axis. And what we want to notice is that if the graph is moving uphill, the slope value is going to be positive. We still have a y-intercept right here located at 0, 1. Again, the x-coordinate on the y-intercept is always going to be 0. This is the y-intercept. And over here we have the x-intercept, or the place where we cross the x-axis, x-intercept. And we see that this is located at -2 input, -2 output 0. And again, the y-coordinate is always going to be 0 as we cross the input or x-axis. We want to notice again that the 1 right here, the value of b in the mx plus b, this has m equals 1/2. M is the coefficient on the x term, and the b is equal to the constant term, or 1, and that's corresponding to the y value, or f of x value, as we cross the f of x axis. And again, just like the previous example, the domain is going to be x is going from negative infinity to infinity, right? Because this arrow here has a horizontal component moving out towards negative infinity on the x or input axis, and towards positive infinity on the x or input axis. And the range is once again going from infinity to negative infinity because of the vertical components of the arrows on the end of this linear function. So f of x is again running over the open interval from negative infinity to infinity. We do get special cases with these graphs. So for example, I have here the linear function given by f of x equals 0x plus 3. And on that first slide, recall that it said, hey, as long as the slope isn't 0, the domain and range are always negative infinity to infinity. Well, this is a case where the slope happens to be 0 right here. So what we see, if we tag our arrows onto our linear function, we see that the x values are going from negative infinity to positive infinity. So the domain in this case is still x is running from negative infinity to infinity. But what we see, because this line is horizontal, that the outputs on this line are always 3. So in other words, if I input -1, my output will be 3. If I input positive 3 over here, my output is still, if I walk over to the output axis, still going to be 3. And in fact, no matter where I put an ordered pair on this line, input whatever, question mark, the output will always be 3. So it turns out that the range in this particular case is going to be f of x isn't running over an interval. I can't describe it in interval notation. F of x is just the set that contains a single number 3. So I use set notation instead of interval notation. I still have a y-intercept right here. Is my y-intercept. And my y-intercept is located at 0, 3. Again, the x-coordinate is 0 at that y-intercept. And this horizontal line has no x-intercept. This will generally be the case with horizontal lines. They will usually not have an x-intercept, and they will have a y-intercept. The exception would be the line f of x equals 0, which would actually be plotted right on the x or input axis, in which case we would have a single y-intercept at the origin, or at the ordered pair 0, 0, and we would actually wind up having infinitely many x-intercepts, in the sense that the the function, the graph of the function overlaps the input or x-axis. So that would be a special case, maybe not particularly interesting. The final example is an example that isn't a linear function, so we want to bring to your attention that not every line that we can draw in the xy plane is a function. So in this case, this is the equation x equals 3. And notice it's a vertical line. So we know it's not a function because it does not pass the vertical line test. Clearly does not pass the vertical line test. And in fact, it's not only is it not a function, but we cannot write it in the form f of x equals mx plus b. This can't be done. It just gets x equals 3. Notice there's no y or f of x piece in this. There's a sense in which the coefficient on the f of x is a 0. Not passing the vertical line test, we could also think of it as from an input perspective. So remember, to be a function, you need to have one input corresponding to exactly one output. In this case, 2 corresponds to infinitely many outputs. So for example, when you input 2, you output 1. But when you input 2, you're also outputting a 3, and you're outputting a -1. In fact, if you input 2, you get every possible number on the vertical axis as an output. So this is one where we would say the domain for this equation x equals 3, well, look, x equals 3. So x isn't running over an interval, it is a single value. So I'm going to use set notation to say x is an element of the set that contains a 3, but the y values, this is the y-axis, the y values, clearly this equation is going infinitely far in the positive infinity direction and infinitely far towards negative infinity. So the outputs, or y values, are running over the interval from negative infinity to infinity. And notice I didn't use the function notation here, whereas in the previous examples I did allow myself to use function notation because we were working with functions. So thus ends our brief introduction to linear functions.